Thank you very much, David. So thank you very much for the invitation. It's a great pleasure to present this work here. So this is joint work with my collaborator, Ori Masauri, who is working at Aalborg University in Denmark. And we are actually currently working on a revision of that paper. So comments and suggestions are most welcome, because now is a good time to incorporate them. So the topic of my talk is non-parametric estimation of trawl processes. I'll talk about the theory of this and also some applications. And I have already a little picture here which shows in which direction we are going. So we are looking into essentially time series modeling, and we want to develop a nice modeling framework for certain types of time series. So time series arise in many applications. So when we started off this project, we were particularly thinking of count type series, okay? So where you have integer valued observations or really count. So you want to, for example, count number of people who have a disease, or all sorts of different applications. I will show you a different financial application in the end when you think of high frequency financial data, where you can only trade essentially on a grid, essentially in terms of the values the process can take. You also have essentially integer value data. So there are lots of different kind of applications where time series of counts feature. And one of these, so we are looking at this from a continuous time framework. Obviously, traditional time series literature is in discrete time. We wanted to look at this from a continuous time angle, and the question is obviously why? Because obviously many physical phenomena evolve continuously in time, so it's very natural to come up with a continuous time model. Also, if you're interested in different kind of discretizations, also potentially non-equidistant discretizations and so on, then the continuous time framework just gives you more flexibility. So then there was an earlier work where Ole Bandorf-Nielsen and co-authors, they looked at just integer valued Levy processes. So as a first, starting point to look into applications in this kind of count data context. But if you're familiar with Levy processes, then you know that they have independent increments, and this is often too restrictive as an assumption if you want to do real-time series modeling. So you want to allow for serial correlation and also ideally some interesting patterns of serial correlation. And this is essentially where the class of trawl processes comes in. So trawl processes as such were first developed by Ole Bandorf-Nielsen in a paper from 2011. And then the class of integer value trawl processes was then essentially brought forward in a paper in 2014. So this is a joint paper with Ole Bandorf-Nielsen, Neil Shepard, and Asker Lunde. And this was all kind of framed in a univariate setup. And then a bit later, I looked into essentially multivariate extensions of this as well. So if you have a true multivariate application, you can also use these kind of trawl framework. So what's now the aim of this particular project? Okay, so these trawl processes, and I will define them very soon what they are. They have been now around for some time. And so far, people have mainly looked at fully parametric specifications and parametric methods for actually estimating the model parameters. So the aim of our project now is to come up with a non-parametric estimation theory. Okay, so there is something which we will call the trawl function, which we don't know and which we are interested in. And that's essentially the component of the model which determines the serial dependence. So we want to come up with a non-parametric estimator for that trawl function, and that characterizes what we call the trawl set and the serial dependence. And then we want to come up, so this is the theory part, the asymptotic theory for that. We want to prove that our estimator is consistent. So we will derive a weak law of large numbers. And then we also want to derive a central limit theorem to have some sort of asymptotic Gaussianity. And in order to derive that, these central limit theorems, we will work under a combination of what we call an infill asymptotics, where the width of the interval over which you observe the data becomes smaller and smaller, but also long span asymptotic, where essentially the time interval over which you observe also becomes bigger, okay? And you have to balance these two rates in a certain way to make sure that the asymptotics work out. Then what we will see is that in our asymptotic theory, there will be an asymptotic bias appearing, and there will also be obviously an asymptotic variance. So in order to actually use these theorems in practice, we need some estimators for these components as well. This is then what we will later call a feasible central limit theorem. So one where you can actually compute all components based on your data, okay? And And then because this is all an asymptotic framework, we want to see whether this is any good in finite samples. So we have run quite detailed simulation experiments to just check whether it works, and the outcomes are pretty good. And then we wanted to apply the methodology now to a couple of various different areas. So the first one is we wanted to shed some light on how we can do model selection and model misspecification testing in that trawling framework. We also wanted to look at some financial applications. So we're looking at some financial spread data from a limit order book. And then it turns out that there's actually a very nice connection between trawl processes and queues. So I'll show you this kind of little link to the queues as well, if time permits. But so these are the application areas. Okay, so let's get started. So if you look at the literature, so this is a very sketchy overview of the literature. There's obviously much more. So the time series literature overall is much, much bigger. But if you're zooming into, say, the integer value time series context, then you see that I would say there are two dominant approaches essentially in the literature of how people model count time series. There are these discrete autoregressive moving average processes, DAMA processes. They have been developed by Jacobs and Lewis in the late 70s. And another approach, which is now, I would say, more popular, is the one which goes back to the works by Stoitel and Van Haan, which uses essentially thinning operations. Okay, again, so you can come up with autoregressive moving average processes using these kind of thinning ideas, and that leads to these integer valued AR and integer valued AMA processes. Okay, because in a classical AMA model, right, or if you just think of an AR1 process, you have essentially this parameter phi right in front of yesterday's value, and essentially in the thinning, you're essentially tossing a coin, or right, you associate a probability with it, how many of these values you keep or not. So this is kind of this thinning idea. And then there are other approaches, other regression type models, state space approaches, Bayesian approaches. So there are many more around, but I would say these kind of the thinning idea is one which is definitely very, very popular. And this is also the idea we are taking up in the trawling framework. Okay, so when we are defining our trawl processes, we use this idea that we are thinning in a suitable space to come up with our time series model. And so this is what we would claim essentially a first approach of doing this kind of thinning methodology in a continuous time framework. And then I have just a list of papers of colleagues who have looked at trawl processes in recent years. So recently there has been quite some interest in that because these processes are very, very flexible. So as I mentioned, the initial paper was by Ole Barndorf Nielsen from 2011, and there he looked into stationary, infinitely divisible stochastic processes, and the trawl processes are a natural example which fall into that framework. But then it turned out that there was actually similar work at the same time by Wolpert and Brown, and also earlier work by Wolpert and Taku, who looked at essentially what we would call now trawl processes. They just gave it a kind of a different name, but the concept was essentially mentioned in the literature before. But in these papers, the authors were then interested in other aspects, so they didn't really follow up on that in more detail. Okay, so these are, I would say, the first occurrences of these kind of processes. And then people were interested in kind of classical inference questions. How can we estimate the parameters of such models using, for example, generalized method of moments or likelihood-based inference, and also some spectral methods. And I have a list of papers where people studied this. What I want to point out, so initially we have these continuous time trawl processes, but for example, Paul Ducan and co-authors, they looked also into discrete time versions of the trawl processes again, okay, so they also then feature in a discrete time framework, so this is quite a general framework now. Then you can use these trawl processes directly for modeling whatever you want to model, but you can also use them as an input in a hierarchical framework. So we have used them, for example, as latent models in modeling extremes. So to model clusters in extremes, we have essentially a latent trawl process. So there's a paper by Bacro et al. And I have a couple of papers with my former PhD students where we use these trawl processes because they are very, very flexible. And then finally, there was a lot of interest in just the theory of these processes, limit theorems for trawl processes. And there are quite a few now of these papers around, both for discrete time and continuous time trawl processes. Okay, so yeah, it's a growing literature, and we're kind of adding to that. Okay, so what is trawling? Okay, so we started off this project really quite a few years ago, before ChatGPT was around. So if you Googled at the time, you would end up on the Wikipedia webpage of what trawling is. And so Wikipedia says trawling is a method of fishing that involves pulling a fishing net through the water behind one or more boats. The net that is used for trawling is called a trawl. Okay, so I want to now give you a bit of a motivation where that name trawl processes comes from. So we are thinking of that we have a boat. Okay, the boat moves forward in time. It travels in this direction. So I actually had to flip the Wikipedia picture so that it goes the right direction. So the boat goes into this direction. And then we have fish swimming in the sea. They swim in a two-dimensional space. So this is R2, where this direction is the time axis, and this direction is essentially the spatial domain. Okay, so the randomness comes through the fact that the fish are randomly placed in our ocean. Okay, and then we have the trawl. This is this fishing net. Okay, and so the idea is that we are now fishing the fish, we are catching them, and we would count how many fish fall into our net. So if I do integer value time series modeling, I would literally just count how many fish are in there. So in this case, I would have 4 fish in my net. So I would say the value of the process at this point in time is 4, for example. Yeah?
But so the y-axis is any space, any latent space.
Yeah, exactly. But we keep it simple and we just stay in R2. But you could go into higher dimensions if you wanted to do that. Yeah. So there you have a lot of flexibility. So you need at least one more than the time dimension, right? At least one spatial dimension. And okay, and so what we want to come up with a process which is stationary, okay, because I said we want to put this potentially into a hierarchical model. So if there are non-stationarities, we would deal with them later, essentially, but the class of trawl processes we define will be a stationary class of processes. So in order to achieve that, obviously, we put some restrictions on how we place the fish in the sea, but we also put restrictions on the shape of that trawl net. So in particular, we say that the shape does not change, okay? So we fix the shape at, say, 0.0, and then we are just moving it along, okay? So we keep in mind that that boat moves forward in time, and the shape of the fishing net would not change, okay? So we always have the same size, same shape, which we use for fishing our fish. What is not completely in line with the real trawling framework is that we would actually let the fish escape again. Okay, so if the fish reaches the boundary here, this is where the picture is misleading because it looks like now the fish is swimming the other direction. But actually, if the fish hits the boundary, we let it go out. And when it goes out, then the process drops again by this amount, in our case by 1 fish, right? So in some sense, we would have here the new fish entering very soon. So it goes from 4 to 5. This fish exiting soon, then it goes down again. Okay, so that's essentially how the mechanism works, and that's where the name trawl process comes from. Okay, it comes really from this kind of fishing picture. It wasn't developed to actually model real fish or anything, but it has a nice kind of, I mean, I think you get a nice intuition of what's going on here. And then obviously you could say it's maybe a bit too simplistic to consider only fish of the same size. So we will later consider small fish and big fish, right, to have a bit more variety of how we model things. But this is essentially where this kind of trawling idea comes from. So now we should make this a bit more precise, right? So we have to put this into a mathematical framework, and we have to define what we now actually mean by this trawl process. So we define our stationary integer value trawl process as a stochastic process xt. T is now continuous time index, which is defined as L evaluated over AT. L is what we call a Levy basis. So if you're familiar, say, with the Brownian motion or Levy process, you can just think of this as an extension to a spatial temporal setting. A Levy basis is a random measure which is independently scattered, and it's infinitely divisible. And we denote it by L here. And then we define an integral where this I stands for indicator function, where we have a set A. So the A is now the fishing net at time 0, okay? And I'm just checking whether the points x, s minus t fall into A. If so, then this indicator is 1, otherwise it's 0. So essentially now you're counting essentially which points fall into the set. We make the assumption that this L is homogeneous, so this makes things a bit easier, and which you will see in the following. So if we make that assumption that this noise, so this is really where the stochastic part comes from, right? This is the random noise. So think of a Poisson random measure of Brownian noise or something like that. So if I make the assumption that it's a homogeneous Levy basis, then we have a characteristic triplet associated with it, which we call gamma, b, and nu. And that means that we have a nice representation of the characteristic function. And this is where the beauty of these processes really comes in, essentially. If I want to, so this, you see the expectation here of this exponential is just the characteristic function. Then I take the log and I get the cumulant function of that Levy basis evaluated over set A. And this is now very particular to the trawl processes, that this cumulant function factorizes into the Lebesgue measure of A. So this is the size of the fishing net times psi of Z, where psi is the cumulant function of an infinitely divisible random variable. So so this is very nice because you have, as you see now, we are essentially splitting the marginal distribution, which is described by psi, and that fishing net, right? They are essentially modeled independently of each other, and this gives us a lot of flexibility later in the modeling framework. I colored some things in blue. The blue bits you need if you wanted to really study trawl processes in R, right? If you wanted to have potentially a Gaussian noise and a drift term, or infinite activity jumps. If you just wanted to be in a classical, say, compound Poisson framework with integer valued jump sizes, then the red formula is the one which you get, okay? So it's much simpler. So if you've seen a characteristic triplet of a Levy process before, then you see it has exactly this form, right? Where we have a drift part, a Gaussian part, and then the jump part, essentially, where you have to compensate the small jumps if they are there, essentially, to make sure that this integral doesn't explode. Okay, so this is essentially the characteristic exponent of that, what we will later call the Levy seed, okay, of a random variable which determines the marginal distribution of our trawl process. And in addition, we have our trawl set. So this is defined as a set A. So you can think of A as A0. This is the fishing net at time 0, okay? And then if you want to look at the set at time t, you're just, we do this plus t0, that means translated in time only, okay? So you're just pulling it along in time. You're not moving it up or down in space, right? You're just pulling it along in time. And this is what this notation means, okay? And then we put some assumptions on the trawl function. So we say that A is continuous, non-increasing and integrable, and that fishing net, the trawl at time 0, is defined in this form. So here the R component is the time component. So we say A is A0. So we only care about the things in the past, okay, time up to time 0, essentially. And in the space component, think of Y as the fish. The fish are bounded below by the time axis and above by that fishing net boundary, okay, which is A of minus R. And the aim now of the project will be to estimate A. Okay, so we want to estimate that boundary function, the trawl function. A little remark why we all like the trawl processes so much. There is some sort of universality property which says that you can essentially give me any infinitely divisible distribution, your favorite one, whether it's a Gaussian, a compound Poisson, or you name it, okay? You can also give me any correlation function you want to have, but we have to put some restrictions on it. We need the covariance function to be differentiable and non-increasing and convex. And if you give me your favorite covariance function in that framework and your favorite infinitely divisible marginal law, then I can construct a trawl process which has that marginal law and that covariance function. Okay, so this is a very nice framework and gives you a lot of flexibility from a modeling perspective. Yeah, so I'll show you this in a second because the covariance function is determined by that A. So we will see that now, I think already, yeah, after the pictures, yeah. So this is just, oh yeah, yes, please. The R is the time. Oh. Yeah, so this would be the time axis, right? So we are thinking now of essentially the fishing, so fishing nets like that, right? And so here I have essentially t equal to 0. So I just, because later I want to translate with t, I say R is smaller equal to that 0, essentially. Okay. and the y is then the spatial variable here. Okay. Okay, so I want to essentially show you the same picture like the one with the fish, but now in this more formal mathematical framework. So I give you an example of a Poisson exponential trawl, where the marginal distribution is just Poisson, as we know it, okay, our favorite Poisson law. And the boundary of the fishing net is this exponential function here, okay? So what you see now is we have the points, which were the fish before. They are all of the same size. They are in space now. So this is the time axis, this is the space axis. So if you were to project the black dots down onto the time axis, you would really just get the arrival times of a Poisson process, okay? But they are placed in space and they are actually uniformly distributed here in this case on 0, 1, okay? And then I have my trawl, my fishing net. And so I want to now show you how I get the path, right? The process out of this construction. So in the second picture, you see the sample paths associated with this construction. So essentially, remember, we have to count 1, 2. There are 2 dots, and you see the value of the process is 2 at this point in time. Then you're pulling along that fishing net, and then you go, for example, to number 18 here. Then we count 1, 2, 3, 4, and this number 5 point is coming in very soon, right? So you see we are at 4, and we're going to move to number 5, to level 5 very, very soon, right? So you see essentially how the construction works, and then the minute the dot goes out, then the value goes down again of the process. Does that make sense from the picture? And again, this is just the Poisson framework where, you know, the process can only go up by 1 or down by 1. And that's often too simplistic, right? Often you want to have something more interesting. And so this is where, for example, the extension to the negative binomial marginal law comes in. So the negative binomial distribution is widely used for integer valued modeling because it allows for over dispersion where the variance can be bigger than the mean, whereas in the Poisson case, both are the same, right? So it looks quite similar. The only difference now is that the dots have different sizes. So you could also think of this as essentially a marked point process where the mark tells you now how big the fish is essentially. And but the construction is the same. You would check which dots fall into the trawl set. And then you're not just adding the number of dots, but you add the marks. Okay, so you're adding the sizes of the fish together, and that gives you then the value of the process. And that's why you see now the scale here is a bit bigger than before. So you get bigger fluctuations here. In this case, they don't have to be, but here, because I wanted a negative binomial marginal law. Yes. Exactly. So for the formal was Poisson marginal, exactly, where all the sizes were 1. Here, so the construction, the negative binomial has a representation as a compound Poisson where the jumps follow a log distribution. So if you use a logarithmic distribution for the jump sizes, then you get negative binomial coming. It was just 1. Yes. Yes, so essentially we are generating the same points, right? But I have to say whether the marks are just 1 or whether they follow a more fancy distribution in some sense, yeah. And you could do this also non-integer valued, right? But I think, you know, just maybe for the purpose of this talk, we can restrict ourselves to this setting. Okay, and now the connection to the covariance function, because that's the crucial bit. So the aim now is to estimate the trawl function A. Okay, so the boundary of the fishing net. And we assume for now that we have equidistant observations of the trawl process, which we denote by xi delta n. Delta n is, you know, the width which we later, for example, have to shrink to 0. So x is by construction, the trawl process is strictly stationary. This is the way how it was defined. Maybe I can show you again, because you see the time dependence comes in by this s minus t. Also, the shape of the trawl does not change with time, so it's constructed as a strictly stationary process. This is actually, when you look at this, this is what we would call a mixed moving average process. It's a special case of a mixed moving average process. Moving average process would be just when I have g s minus t, right? But here I have a second variable in there, and then that we would call it a mixed moving average process. Okay, so it's strictly stationary, and we also assume now that we have a second moment that we can actually compute covariance functions. And then the autocovariance function of this trawl process be denoted by gamma. has a very nice form. It's given by the variance of that infinitely divisible random variable which appeared, in this characteristic function, and the integral of the trawl function where we integrate from h, which is the lag we want to consider in the autocovariance function. Okay, so this is the very important property of that trawl process. And if you wanted to compute the autocorrelation function, you would divide by, again, variance of L prime, and then the integral from 0 to infinity. So the variance terms essentially just cancel out. Okay, but you see now we have a product, right? And we want to estimate one side of the product. So obviously we have some sort of identifiability issue. So you have to fix one side or the other to be able to identify things. It doesn't really matter which one you fix. So we decided to fix the variance of L prime to be equal to 1. You could also say you want the integral from 0 to infinity to be equal to 1 or to any constant, really. But we fixed the variance to be equal to 1. This is not really a strong restriction because it does not fix the variance of the process, right? The variance of the process can still take any value because I have full flexibility in that second component. So yeah, that wasn't on the slide, but it's the random variable which has this distribution or this characteristic function. So we call it the Levy seed associated with that Levy basis. Yeah. Okay. Okay, and now, I mean, when you see that, and the aim is to estimate A, and we are observing essentially the integral of A, then it's very natural to just say differentiate, right? We differentiate that, and then that should give us an estimator of the trawl function. And this is exactly what we do. So we note that the derivative of the covariance function is just minus the trawl function because of that lower bound here. And then a very natural estimator to consider is to say, well, just take the finite difference, right? We just take the difference divided by delta n of the empirical autocovariance function, and that should give us an estimator of the trawl function. And we do that in a kind of, we estimate it as a step function. So our observations are on this delta n grid. So at each point, we essentially change the estimator, and in between, we keep it constant. Yeah. Yeah, yes, okay, yes, we do. It's not, yeah, exactly. So it is positive. Yeah, otherwise we are in trouble. Yeah, exactly. No, it's positive. We assume continuity, things can, yeah, so, but the positivity is important because we take, I mean, we're only considering sets of this type, right, which are bounded below essentially by the time axis. And the empirical autocovariance function is really just taken the traditional way. So there's nothing special about that. And this estimator you can take for any t, but what we find is that we would recommend that if you want to estimate the trawl function at time 0, that you take a slightly different estimator. So this is essentially the realized variance scaled appropriately by 2 delta n. And it's very difficult now just from the formulas to see why this is better. But what we later find is that the limit theory for the case t equal to 0 is slightly different. And if we take that particular estimator rather than one coming out of the general approach, then the limit theory works in all cases. So it's more robust, essentially, to use that estimator for A0. Okay, and now you see, obviously, for this empirical covariance to be good, right, we need n large, right? For differentiation to make sense, we need delta n small, right? So now that's where these kind of double asymptotics come in, okay? So this is the construction of the estimator, and now I want to show you the main results. So first of all, we have to prove consistency. So we assume now that n goes to infinity. This is the number of observations. Delta n is the grid over which we observe. That goes to 0. N delta n is essentially the final endpoint, right? The final observation. So you also send that to infinity. So the observation window becomes bigger and bigger. Okay. And under this setup, we essentially get consistency. So we have this assumption. We assume that variance of this Levy seed is 1. We have a fourth moment condition as well. And then we get that our proposed estimator converges to the true trawl function in probability. And this is pointwise. Okay, this is for fixed t. So we don't yet have a joint convergence results over all t. So this is for fixed t. We get the consistency. So that's very nice. And now I want to show you the asymptotic Gaussianity. So there, things become more complicated and we need more technical assumptions, which I have in the appendix, and I'm happy to discuss them later. But for now, I'm just saying there are some more assumptions we need for our central limit theorem. And the type of limit theorem we get will depend on essentially the limit of n times delta n to the power 3. So this is a term which appears in our computations for the central limit theorem, and this can take, you can be in 3 scenarios. So we take the limit of this, we call it mu. So the limit can either be 0, it can be a positive number, or it can be equal to infinity. And depending on what you get there, you get different outcomes. So the first case, which is kind of the nicest, if mu is equal to 0, then we get essentially a classical central limit theorem. Okay, your estimator minus the truth scaled at the appropriate rate, which is in our case square root n times delta n, converges to something normal where you have an asymptotic variance, and the asymptotic variance is also given in a closed form. Okay. And so you see there is essentially the fourth moment entering or fourth cumulant of the Levy seed. So this only appears obviously if there are jump terms in there. If it was a purely Gaussian setting, this term would disappear. If that limit here, that mu term, if this is a positive number, then an asymptotic bias appears. And you also need to allow for some discretization error. So we are not centering this by AT, but this discretized version here, everything else is the same. So we get the same Gaussian random variable in the limit, but there is this additional bias term where the mu features, okay, this was the limit of n times delta n to the power 3, and the derivative of a features as well. Okay, so that's a bit curious. And then the final case is mu equal to infinity, where you just get a limit in probability. So from a practical perspective, the scenario 1 and 2 are the interesting ones, right? And where we get essentially a Gaussian limit in the end. Obviously, you know, in practice, I mean, whichever grid, you are always on a finite grid, right? This delta n is just a fixed number, n is a fixed number. So even if asymptotically these things go to 0, for example, it's in finite samples is a positive number. So you are actually kind of finding yourself in this kind of framework that there is some sort of bias term appearing in the limit theorem. So even if asymptotically you're in scenario 1, we find in our simulation studies that it's always good to account for this bias term in your estimation, because then you're not making any mistake. Yeah?
Estimation, you have 2 steps, right?
Yeah.
Estimation,
Yes.
then you have the derivative.
Yes, exactly, exactly.
So what comes from what?
Yeah, okay, and I should point out, so first, I mean, so for the covariance, I need the long span n, right? So this, and for the differentiation, I need the delta n to be really small, but then I need to balance things out in the right way. And this term n delta n to the power 3 appears in our computations of these kind of ratios we are considering here for the trawl estimate, and we need to control it. Now, depending on what comes out, we get different limits. These kind of discretization things come from the fact that we are essentially approximating this a function. This comes from an integral where the lower bound is this one and the upper bound is this one plus delta n essentially of ASDS. So essentially we are approximating an integral of the a function over a tiny interval of length delta n, and that's where these terms essentially come from. What is very curious, and this is always causing surprise, if I was to study the limit theory for the covariance, right, then it would actually really matter whether the process has long memory or not. But the interesting thing is, you see, I mean, obviously I haven't shown you all the assumptions, but there is no assumption on the memory to get these limit results. So even if the trawl process has long memory, these results hold, whereas they would not hold in the covariance case where you would need to adjust for the memory. Yeah, yeah. No, the covariance can still be unbounded. So I'll show you some examples in a second. So it has bounded Lebesgue measure, but we're not cutting it off. Yeah, It's only bounded measure. I'll show you an example. So it can have truly long memory. And this is surprising because initially you would expect that we have to say if short memory then this, if long memory then this, but we don't get that. And we have now also an explanation why this is the case. It's the way how these kind of terms, the increments feature in our derivative of the covariance function, that the asymptotic result is independent of the memory. So that's very curious, and I'll show you this example of a long memory case in a second. And then, so this is what we would call an infeasible limit theorem, right? Because this asymptotic variance is not known, also that bias term is not known to you, so you wouldn't be able to compute it from the data. So the final step is now to obviously find estimators for these objects. And you see, I mean, it's quite intuitive. In the asymptotic variance, we have, again, integrals of the A function appearing. We have already estimated A. So we would expect we do a plug-in estimate, right? And hopefully things work out. And so you have to be a bit careful with this plug-in estimate. So we need to essentially do some adjustments over which grid we are computing this plug-in estimate. But if you do that correctly, you get a plug-in estimate, which gives you an estimator for the asymptotic variance. And similarly, we have already differentiated our covariance function. I can numerically differentiate again. If you do that in a nice way, then you also get an estimator for the asymptotic bias. So assuming we have these estimators now, I'm just putting hats over these terms, then we get essentially what we would call feasible central limit theorems, right? So now I have a feasible central limit theorem for my trawl function, where in the end I have standard normal random variables. And this is obviously now something I can test in simulation studies, right? So we have now tested this in much detail for various different marginal distributions, different trawl functions, in particular the ones with the long memory, right? Because we wanted to see how well this works, and it has all worked out quite nicely. We still find that it's a bit trickier in the long memory case, although theory, I mean, if you crank up the n high enough and the delta n small enough, right, you get really nice standard normal limits, but you obviously have to be closer to this asymptotic regime to see that, whereas otherwise the final sample performance is already working quite nicely for the, I would say, simpler trawl functions. Okay, so that's kind of, I would say, the main theoretical result. And now I wanted to just briefly recall, we have done the simulation studies, with the different marginals, different trawls and so on. And we found that using this bias correction is actually very advantageous. So we would always recommend that you make this bias correction, that you subtract this here. Even if you are in this kind of regime, it doesn't hurt essentially to subtract this corrected bias, and then you are essentially on safe grounds, I would say. And and we find the short memory case, the coverage probabilities were really good. We have some small greater deviations from the theoretical coverage for long memory, but it wasn't bad. Okay, so it's still looking very reasonable. So now I wanted to show you a couple of applications. Okay, so what can we do with it? So one question is, for example, because so far people have looked into these parametric models, right? Fully specified parametric trawl functions like an exponential function and so on. And then obviously you might ask, why do I need a non-parametric procedure? So we would now argue that it's actually much easier to identify more complex shapes in the trawl function with that non-parametric estimator, because in particular, if you think of trawl functions like this one here, where you have, for example, this is a piecewise exponential, okay, two exponentials which just break here. Essentially, you can think of other scenarios where the shape just changes quite rapidly over at certain breakpoints. And so this is a piecewise exponential. This is an exponential function. And in both cases, I show you the autocorrelation function associated with it, which is just the integral. And you see visually, they obviously look very, very similar. And when you do a classical estimation theory, the classical theory so far was based on the autocorrelation function itself. You would not be able to pick up these kind of more complex shapes. Yeah. So we can smoothen over that point. Okay, so this is so for consistency we just need essentially boundedness, which is fine. This particular one we can have essentially an epsilon environment where we smooth over, which we are currently investigating. So you can smoothen that, but in practice you wouldn't notice, right? Because I can put that window which I put around to smoothen things. I can make it so small that you effectively don't see it. Yeah.
But are you saying that the true function is smoothed, or is it?
Yeah, the true function is smoothed, right?
Okay.
Yeah.
What happens if it's not? Do you have something that breaks? Because surely.
For the consistency, no, it wouldn't break. Asymptotic normality, in particular, later when derivatives come in, then we obviously have to be careful, right? So, but for consistency, it wouldn't break. Yeah. So essentially, so yeah, if you fit the true model and the exponential model to the autocorrelation function, you would not be able to distinguish them essentially. The other thing, yeah, so what you can do now with our result, you can do essentially misspecification testing for fixed lags, okay? You can't do it jointly, okay, because this is for fixed t, essentially. So you can do essentially in an exploratory data analysis, you could plot, you could now compute our non-parametric trawl estimate, you can put the confidence bounds for each point, and for example, you can pick your favorite parametric model, you can estimate it, you can superimpose, and you check whether you have deviations essentially from these confidence intervals. So if I'm testing the hypothesis that AT follows a particular parametric form at that particular point t, then our theory gives us the limit distribution of that test statistic, okay, under the null. So I'll show you a picture which I think shows you a bit better what's going on. So this is just, I mean, obviously we've done that for many parts, but this is just for one path that you see essentially. The red line gives you the true trawl function, which is a piecewise exponential one. The black one gives you the estimated non-parametric trawl function. The blue one gives you the pointwise confidence bounds, 95% based on our theory. Then the purple one is the true model fitted to our estimate. And the orange one is the exponential, so the force model fitted to this. And you see, if you just were to use this now as an exploratory study, right, you see that the orange one curve obviously falls outside our bounds quite a few times, in particular early on. So that gives you already some indication that maybe that is not the best model to use, right? So, but the test specifically would work for one particular fixed t, right? And so otherwise we are placing ourselves into this multiple testing problem where we obviously have to be careful how to adjust. But my collaborator, Ori Masauri, he's currently working on extensions of to get essentially these kind of functionals that you can do joint testing. So there is something in the pipeline, but it's not yet in this paper. Okay, so that's one, I think, nice application. I wanted to briefly show you now the application to the financial data. So here we looked at 4 stocks from the New York Stock Exchange. I will just focus on one stock only, so that we're not running out of time, which is Agilent Technologies with the ticker symbol A. We got the data from Lobster. Lobster is a very nice database of limit order book data from NASDAQ, which you can access via subscription. But there are some data sets on Lobster which everyone can download, but if you wanted to have data for multiple years and so on, then you would need to get a subscription. So we got essentially the first level of the limit order book with the bid and the ask prices, and we wanted to see whether we can apply our trawl model to these prices, because this is an application which has been used quite often in the previous literature. Okay, so these integer value trawl processes have been used in various papers to model essentially high frequency spread data. So the trading hours, so we have 2 years of data. The trading hours are at the New York Stock Exchange are from 9:30 to 4, but you can imagine obviously when the market opens, there's a lot of non-stationarity happening. So we're just getting rid of that first hour. We are not considering this for now. We are essentially looking at the time period from 10:30 to 4. Also, it would be not wise to assume that asset prices follow a stationary process. So we are looking at the spread prices instead, so the difference between the bid and the ask price, because they tend to be much more stationary than the prices themselves. So that's what we are looking at. So we are sampling at a 5-second frequency. I mean, we have the full book, right? So we get each interaction, so we can sample on whichever frequency we want. We sample this at 5-second frequency. We have almost 4,000 observations per day. And we have around 460 days for this stock A for these kind of 2 years of data. We computed the spread, so the difference between bit and ask, and then we subtracted 1, so which was the minimum spread size. So then the values are from 0 upwards. Okay. Yeah, because you can only trade on certain cent values, you know. So it's actually not a real price. So the trading happens on a grid, and that's why it's actually integer valued on that 0.01 grid, cent grid. Yeah, exactly. So that's why it's a nice application. And you know, we picked stocks which don't move that much, in the sense that you really see that grid structure even more in some sense, right? Because you could obviously say, the minute, you know, I mean, there are many applications where the true data is integer valued, but you could approximate by a time series on R, right, quite easily. But if the values are really just between 0 and 5, say, it makes much more sense to maybe have a dedicated model to account for that integer structure in some sense, right? So this is then more a philosophical question, on which level do you switch over. But this is actually data which is truly on a grid, essentially. Yeah, exactly. It's the same units, because I'm just subtracting these two prices from each other, right? So there's no change there. Yeah, exactly. Actually, I don't have a picture now of one path. I should have included a picture of a path next time. I can show you one. So what we want to do is we want to estimate the trawl function now for each state. We want to estimate the trawl function to get an understanding of, you know, how it evolves over time. But we also want to do a little prediction exercise, and because this is part of the program to talk about prediction and uncertainties, I want to do a bit of prediction as well. So suppose now I have observations x0 up to xn minus 1 on times delta n, and I want to predict xt plus h, essentially h steps, or time h, I should say, ahead on that continuous time grid. So the classical forecast formula you would use if you wanted to minimize the root mean square error would be to use the conditional expectation, right? This would be the default kind of candidate for computing forecasts. The problem is now that our trawl process is highly non-Markovian, right? So that conditional expectation is not available in a nice form. So what we do is we work with the Markovian approximation, okay? So we know this is mathematically just an approximation, but we are computing the conditional expectation of xt plus h given xt, although it depends on other lags as well, right? But that's what we are computing. And so my former PhD student, Dan Leonte, he worked out a very nice forecasting formula, which actually shows that this conditional expectation is just a weighted sum of essentially today's value xt and the mean. Okay, and the weights are determined by the Lebesgue measure of A and AH. Maybe I'll give you a little picture here. Okay, so if this is t plus h, then this is at plus h without at. This is the intersection. At, and this is at without, right? So I can essentially split it into these parts, and you see the Lebesgue measure of this guy is the one which features in the first weight, and the Lebesgue measure of, so it doesn't matter. So it turns out actually that the size of both, the Lebesgue measure is the same, features as the weight in the other one. And maybe just to point out, because we have a Levy basis as our random noise, if I evaluate the basis over these disjoint sets, the associated random variables are independent of each other, okay? And essentially all the proofs of our theory hinge on this fact that if I slice things up, I'm essentially dealing with independent random variables, and then you are in business, right, essentially. Okay, so this kind of formula comes, I mean, visually it comes from here, but we can obviously prove properly where this comes from. So what we do is we use our trawl estimate now to compute these, we call them slices, okay? Because I have a function, I can compute the integrals of these functions over certain sets, and I get an estimator. And then, but it turns out that this is actually just the autocorrelation. So I could also just use the empirical autocorrelation as a weight and 1 minus the empirical autocorrelation as a weight. And we can do some parametric models, which is what people have done in the past. If I use an exponential trawl, the autocorrelation function is exponential minus lambda h. And now I wanted to show you the one example which has long memory potentially. So if I take a polynomial, essentially function for the trawl with a certain h here, I get an expression for the autocovariance function or autocorrelation function, which is of this form, 1 minus h. And now depending on which value of h you get, so we need this h to be bigger than 1. But if h is between 1 and 2, you actually get true long memory. And if it's bigger than 2, then you're in the short memory setting. So we can estimate this and essentially see what's happening. Okay, so now we do our forecasting exercise. So we split. We have a test set of, say, the training set of 80% of the data and test set of 20% of the data. And then we always do essentially, here we do 10 up to 10 lags ahead. Okay, so we do 1 step, 2 step, 10 step ahead forecast, and then essentially a rolling window. And we compute the root mean square or the mean square errors for each lag, for each method we are using. And then we want to essentially compare what's going on. And we thought it's kind of nice to maybe visualize things via a ratio of these mean square errors, because then you see so that our non-parametric trawl is at the bottom. So if the ratio is smaller than 1, then this is essentially what we want to. Sorry, no, I said it the wrong way around. We want to see that ours is smaller than 1, exactly, then our method is the better one. And we find that this is essentially the case so that we are doing better than the ACAF-based, the exponential-based. But with the long memory one, this is the more flexible parametric model. We see that we are essentially doing on par. So meaning if you find the right or good parametric model, then there's no benefit or gain to do non-parametric versus the parametric model. So I just wanted to show you the estimate here now of the trawl function. Essentially, these are the box plots of these 400 essentially days where we estimated the trawl function. You see this is decaying fairly fast essentially, and then we are comparing the mean square errors ratios for these various methods. And if it's smaller than 1, then our ratio is our method is the better one. And we are also looking at the weights here, which you see where the autocorrelation function one, the non-parametric trawl-based one, and the long memory model, they are all kind of doing the same job essentially, whereas a wrong parametric one, like the exponential one, which is decaying too fast, is really deviating quite strongly here. So that leads us then, I should probably to conclude that essentially what we would say is that the benefit of the non-parametric method is really that you don't have to do any model selection, right? It's very, very flexible. If you find the right parametric model, then the performance is pretty much on par with the non-parametric one. But if you pick the wrong parametric model, then obviously you get worse results. So a final little outlook on the queue, I wanted to give you just in a couple of minutes, if that's okay. So when it turns out that trawl processes can be linked to MG infinity queues. So M means you have Markovian arrival, G is the service time distribution, which can be general, and you have infinitely many servers. So this link we can make, for example, if you're looking at an integer value Poisson trawl, where you literally just have essentially the fish of size 1 arriving, right? So think of essentially of a traditional queue, and we are counting essentially what's going on. Then we can look at this decomposition of our trawl process, which can be written as this this intersection we have here, plus essentially the counts which happen after time 0, okay? Where that trawl function plays the role essentially of a service time distribution, okay? So you can say the time it takes to service this one person is the time it takes for the, to exit that trawl essentially. So we can come up with a service time distribution which depends on our trawl function. And if I assume that A0 is 1, just to simplify things, and I condition on that at time 0 we have 0 people in the queue, then we get a very nice classical queue setup. And then it turns out that in this queuing literature, people were interested in this busy time distribution. So say your queue is currently has 0 people in the queue, and then people are arriving, and you're asking how long does it take until it's not busy anymore, right? Until there are 0 people in the queue. So you're looking at the busy time, that the value of the process is greater than 0. And it turns out that we can compute this busy time distribution using our trawling framework. And this is very nice because we get an expression. So we get an expression for our busy time distribution in terms of these infinite sums of, you know, the n-fold convolution of our essentially trawl functions. Okay, so the trawl functions feature there. So meaning obviously that you could use potentially this parameter non-parametric estimate for estimating essentially the distribution of this busy time distribution in a queue. And we've run this in the simulation where, you know, the estimated box plots are in black and the truth is in red, essentially, where you see it aligns quite well. We were struggling to find any sort of empirical data which is a true MG infinity queue. I mean, if you're aware of anything which could be used, please do share this. But this is just a final little application. So just to wrap up, I hope I could convince you that trawl processes form a very flexible class of continuous time stochastic processes. They are stationary, they are infinitely divisible, they can capture short and long memory. So depending on what application you have in mind, they can be used for various different things. They can also account for very different kind of tail behavior, right? You can have light tails, heavy tails, and so on. So that's very nice. We developed now the first non-parametric estimation theory for the trawl function, and we find that we have consistency under very mild conditions and asymptotic normality under slightly stronger conditions. But the important thing is that the conditions don't depend on the memory of the process. We got very good results in the simulation study, so we are quite happy with the kind of finite sample performance. And we would say that when you do forecasting or non-parametric estimation, this is really just a very simple and fast alternative to the parametric models, right? It's much faster to compute because I don't have to do any optimization anymore, right? When I'm obviously fitting sophisticated multi-parameter models, I'm doing lots of optimizations. Here I don't optimize anything anymore. I have the non-parametric estimator, and it's often on par. If you find the correct parametric model, you're on par. Otherwise, you're even better, right, if you have the wrong model. So I think there are lots of benefits with going with this non-parametric approach. Thank you very much. Yeah.
Where does the integer
No, so in the theory works for everything, yeah. So I just the motivation when we first started off studying the trawl processes, we started with a purely integer valued framework, but in the theory you don't need it. It works. What I can say is if you're in the purely Gaussian framework, there we have some additional results essentially. So in the Gaussian case, things can behave quite differently. Maybe I can show you here. So if things are truly Gaussian, then this fourth cumulant is 0. So then, for example, if you then that term goes away. And then if we are looking at, for example, t equal to 0, then these two integrals would cancel out. So you would get a degenerate limit. So we have derived some additional results if it's purely Gaussian. If it's purely jump, fine, then we are kind of in that setting. But yeah, no, it's a good point. I mean, the theory does not depend on integer values, this assumption, yeah. Mm-hmm.
So I have a question.
Yeah.
So I think your method several things that need to be prescribed.
Yeah.
Including L.
Yeah, the Levy basis, yeah. Yes.
So in practice.
Yeah. Yeah, so that's the next part one would need to estimate. I mean, in the fully non-parametric, in the parametric literature, there we have really estimated, right? We said, let's try Poisson, no, it doesn't fit. Let's try negative binomial, right? Go through the various kind of cases of integer valued distributions we know, and these are all essentially the class you can consider are the compound Poisson distributions where the jump sizes live on the integers or on the natural numbers, right? So this is the class you can consider, and then you would need to do classical goodness of fit testing here. We have not, so currently in this project we are entirely looking at the trawl function estimation, right? So we are not doing the empirical distribution of L yet, right?
Do you think there could be some identifiability issues with A and L at the same time?
With A and L, well, we put it's similar to this assumption, right, that we put the variance to be equal to 1, right? So I have to fix the moments of 1 versus the size. So this definitely we have to do. But it doesn't matter which one you fix, but one of the two you have to fix to identify. Yes, because what you will see is, because we have this expression, right? So the Lebesgue measure of A goes into each part of the distribution. So to pull them apart, you need a condition there. I mean, what we are currently looking into a little bit is we want to improve that forecasting formula, right? So we are currently regressing only on today's value. You can obviously think of a similar thing to regress on the last n, right? Values essentially have a more sophisticated framework. And there, my former PhD student, Dan Leonte, he's working on extensions of this to actually use some sequential Monte Carlo sampling procedure to sample from these different slices and then actually do a probabilistic forecasting, right? Then it's not a point forecast, but probabilistic forecasting. I mean, that's what we are working towards. That would be the ideal outcome. It requires JAX, right? It requires much more kind of different kind of computational efforts, essentially. But that would be obviously a very nice thing then to have, right? And he has already explored that to some extent in his thesis.
So my second and last question is very pragmatic.
Yeah.
Did you compare to real values for the examples that you're looking at?
Oh, with it, okay. No, I mean, so it's the answer not for these stocks, right? To just but in some sense, because in the forecasting exercise, it doesn't really matter, right? Because I'm just estimating, I'm taking the mean. That's actually good. Maybe I should point this out briefly. So there is an issue. If you look at this forecasting formula, does not guarantee an integer valued forecast, right? Because these things are not integer valued and the mean is not integer valued either. So actually this conditional mean is not integer valued. So that's why also from this perspective, a probabilistic forecast where I can then take the mode or something like that is probably better in a kind of purely integer value setting. You can obviously do rounding and things like that, right? There are some cheap fixes. But when I do just the prediction exercise itself, I don't use, right, what kind of marginal distribution comes in, because I'm really just taking the observations and the empirical mean. So in that sense, it's kind of robust, but I could, okay, I could estimate, I can make an assumption it's Gaussian, and then I take the Gaussian mean, okay, but it would still not change much.
I meant more, taking some classical, like, real value time series approaches, just
right. No, it's a complete, no, I mean, that's definitely, on the benchmarking level. No, I mean, that's, so currently we are benchmarking within the class of trawls, right? And also to the naive forecasts and things like that. But we have not really compared to others. I mean, I think would be more the integer valued ARMA processes, also some of these other maybe integer valued processes. Yeah, but one can definitely compare with many more. I agree. Thank you.